Here is a combined summary of the 2 pages. This research paper investigates weighted linear hyperbolic cross-polynomial approximations of functions on road from weighted Sobolev spaces of mixed smoothness and their optimality in terms of Kolmogorov and linear n-widths. The approximation error is measured by the norm of the weighted Lebesgue space LQ, W, road. The weight W is a tensor product Freud weight, which is a critical parameter in the weight. The paper begins by introducing the notion of weighted Sobolev spaces of mixed smoothness WR, P, W, road, and their corresponding norms. These spaces are defined using the weighted Lebesgue spaces LP, W, road, which are characterized by a specific norm. The norm of a function in WR, P, W, road, is defined as the sum of the LP, W, road, norms of its weak partial derivatives. The paper also introduces the concept of linear approximation, where a central symmetric compact set F in a Banach space X is approximated by elements from a fixed finite-dimensional subspace L. The goal is to find the best linear approximation, which is characterized by the Kolmogorov and linear n-widths. For 1 is less than or equal to p, q is less than or equal to infinity and d equals 1. The paper proves that the polynomial approximation by Delavalle-Poussin sums of the orthonormal polynomial expansion of functions with respect to the weight W2 is asymptotically optimal in terms of relevant linear n-widths lambda n and Kolmogorov n-widths dn. For 1 is less than or equal to p, q is less than or equal to infinity and d is greater than or equal to 2. The paper constructs linear methods of hyperbolic cross-polynomial approximation based on tensor products of successive differences of dyadic-scaled Delavalle-Poussin sums. These methods are counterparts of hyperbolic cross-trigonometric linear polynomial approximation. The paper provides upper bounds for the error of these approximations for various pairs p, q with 1 is less than or equal to p, q is less than or equal to infinity. For some particular weights W and D is greater than or equal to 2, the paper proves the right convergence rate of lambda n and dn, which is performed by a constructive hyperbolic cross-polynomial approximation. The paper's results have implications for weighted approximation, hyperbolic cross-polynomial approximation, and linear widths. The problem of approximating functions with mixed smoothness on a compact domain is considered. The Kolmogorov NWIDTH and linear NWIDTH are introduced as measures of the optimal approximation error. The Kolmogorov NWIDTH is defined as the infimum of the supremum of the approximation error over all subspaces of dimension at most n, while the linear NWIDTH is defined as the infimum of the supremum of the approximation error over all linear operators with rank at most n. The paper focuses on the linear hyperbolic cross-polynomial approximation of functions with mixed smoothness on road. The functions to be approximated are in weighted Sobolev spaces WRP, W, road, and the approximation error is measured by the norm of the weighted Lebesgue spaces LQ, W, road. The results imply upper bounds of the high-dimensional linear n-widths and Kolmogorov n-widths. The main results of the paper are presented, including the definition of the generating weight W and the notations R lambda, dl, p, q, and R lambda, p, q. The Delavalle-Poussin hyperbolic cross-sum operator Vichy is introduced, and it is proven that the approximation error of Vichy f is bounded by a constant times the norm of f in WRP, W, road. The paper also proves that the linear n-widths and Kolmogorov n-widths are bounded by a constant times n minus R lambda, p, q, log n, R lambda, p, q plus 1, q, d minus 1, for p equals q, and by a constant times n minus R lambda, p, q, log n, R lambda, p, q plus 1, d minus 1, for q equals infinity. In the unidimensional case, the right convergence rate is proven to be n minus R lambda, p, q. The linear polynomial approximation method Vichy-n is introduced, which is based on the tensor product of successive differences of dyadic-scaled Delavalle-Poussin sums of the orthonormal polynomial expansion of f with respect to the multivariate weight W2. The paper also proves the right convergence rate for lambda equals 2, 4. The results of the paper provide a generalization of previous results on the approximation of functions with mixed smoothness and imply upper bounds of the high-dimensional linear n-widths and Kolmogorov n-widths. The paper also introduces a new linear polynomial approximation method V-N, which is based on the tensor product of successive differences of dyadic-scaled de Laval-Poussin sums. The paper is organized to study linear polynomial approximations in the norm LQ, W, R, of univariate functions from WRP, W, R, by de Laval-Poussin and Fourier sums of the orthonormal polynomial expansion of functions with respect to the univariate weight W2. The approximation error is measured in the norm of LQ, W, R, and upper bounds of the error are given for 1 is less than or equal to p, q is less than or equal to infinity. The paper also proves the asymptotic optimality of these approximations in terms of linear n-widths lambda n, WRP, W, R, LQ, W, R, and Kolmogorov n-widths Dn, WRP, W, R, LQ, W, R. For 1 is less than or equal to q is less than or equal to p less than infinity. In the context of multivariate functions, the paper constructs linear methods of hyperbolic cross-polynomial approximation and gives some upper bounds of the error of these approximations for various pairs p, q with 1 is less than or equal to p, q is less than or equal to infinity. For the particular weights w with lambda equals 2, 4, the paper proves the right convergence rate of n-widths lambda n, WR2, W, rho, L2, W, rho, and Dn, WR2, W, rho, L2, W, rho. The notation used in the paper includes x equals x1, xd, for x element of rho, x, p, equals summation text dj equals 1, xj, caret p, caret 1, p, 1 is less than or equal to p less than infinity, and x, infinity, equals max 1 is less than or equal to j is less than or equal to d, xj. The inequality x is less than or equal to y, x less than y, means xi is less than or equal to yi, xi less than yi, for every I equals 1, d. The paper uses letters C and K to denote general positive constants which may take different values. The approximation error is measured in the norm of LQ, W, R, and upper bounds of the error are given for 1 is less than or equal to p, q is less than or equal to infinity. The paper also proves the asymptotic optimality of these approximations in terms of linear n-widths lambda n, WRP, W, R, LQ, W, R, and Kolmogorov n-widths Dn, WRP, W, R, LQ, W, R. For 1 is less than or equal to q is less than or equal to p less than infinity. The text discusses the approximation of functions by polynomials and the properties of certain operators. It begins with the definition of the best approximation of a function f by polynomials of degree at most m, denoted as e_m, f. The authors then present several inequalities involving this best approximation, including the relationship between the L_p norm of the best approximation and the W_r_p norm of the function itself. The paper also discusses the properties of the operators v_m and s_m, which are used in the approximation process. These operators are shown to satisfy certain inequalities, such as the Markov-Bernstein type inequality and Nikolsky type inequalities, which provide bounds on the derivatives and norms of polynomials. The authors define the unidimensional operators v_m, k and s_m, k, which are used to represent functions as series. They prove that these series converge absolutely in the L_q norm and provide norm estimates for each term in the series. This leads to a theorem stating that the L_q norm of the difference between a function and its approximation by polynomials of degree n is bounded by n_r_lambda, p, q, where r_lambda, p, q is a positive constant. Finally, the paper presents a corollary that provides bounds on the approximation numbers of the identity operator between certain function spaces. This corollary shows that the approximation numbers are equivalent to n_r_lambda, p, Q, which demonstrates the effectiveness of the polynomial approximation method. The paper discusses the approximation of multivariate functions using weighted hyperbolic cross-linear polynomials. It begins by proving a series representation for functions in the space LQ, W, R, with absolute convergence and norm estimates. This is followed by a theorem that provides upper bounds for the error of these approximations and linear n-widths, as well as Kolmogorov n-widths for various pairs of P and Q with 1 is less than or equal to P. Q is less than or equal to infinity. In the context of hyperbolic cross-polynomial approximation, the authors introduce orthonormal polynomials with respect to univariate Freud-type weights and define divariate polynomials as the product of these univariate polynomials. They also provide Parseval's identity for these polynomials. A lemma is presented which states that if a function f has derivatives in LP, W, ρ, up to a certain order, then its derivatives of lower order are also in LP, W, R, E, for almost every z element of ρ minus E. This result is used to construct approximation operators for functions in LP, W, ρ, using the Smoleic algorithm. The authors define omnidimensional and d-dimensional operators v2k, vk, and ek, which are used to approximate functions in LP, W, ρ. They prove a lemma that establishes an upper bound for the error of these approximations in terms of the norm of the original function in WR, P, W, ρ. Finally, the paper discusses the right convergence rate of n-widths and Kolmogorov n-widths for certain weights and pairs of P and Q. This is achieved by establishing connections between the approximation error and the norms of the original function and its derivatives. The analysis begins with a demonstration of the absolute convergence of a series in the space LQ, W, ρ, leveraging theorem 2.3 and lemma 3.1 to establish the inequality, vextend double E, K1, K2, F, vextend double LQ, W, R2, is less than or equal to C2 minus R lambda, P, Q, K2, 1, vextend double EK1F, vextend double LQ, W, R, vextend double LQ, W, R. This is further simplified to C2 minus R lambda, P, Q, K, 1, barred BLF, barred BLWRP, W, R2, where K right pointing arrow infinity if and only if Q right pointing arrow infinity for every I equals 1, D. Lemma 3.3 states that for every f element of WRP, W, ρ, the function f can be represented as an absolute convergent series in LQ, W, ρ, and provides an upper bound for the norm of the operator VKF. The proof involves representing the operator Vk as a sum of ek, E, F and applying lemma 3.2 to derive the desired inequality. Furthermore, it is shown that the series converges absolutely in LQ, W, ρ, and the function f can be approximated by the partial sum V2kF. The operator V(she) is introduced as a linear bounded operator in LQ, W, ρ, defined as the sum of Vkf over k element of ND0 with k, 1 is less than or equal to she. The rank of V(she) is calculated to be h, she, approximately equals 2xxd-1, where h, she, is the multi-index set consisting of non-negative elements of the step hyperbolic cross h, she. This approximation is referred to as weighted hyperbolic cross-polynomial approximation. Lemma 3.4 provides an inequality for the norm of a function f element of LQ, W, ρ, represented by a series of phi k element of P2k, which converges in LQ, W, ρ. The inequality involves a constant c depending on lambda, p, q, and d, and holds whenever the right side is finite. Theorem 3.5 establishes that for any function f in the Sobolev space WR, P, W, ρ, and for she greater than 1, the difference between f and its approximation V(she) f can be bounded by the norm of f in the Sobolev space. This theorem provides a key insight into the approximation properties of the linear operator V(she), which is crucial for understanding the behavior of functions in the Sobolev space. Theorem 3.6 extends this idea to the context of NTERM approximation. It states that the nth approximation number lambda n can be bounded above by the supremum of the norms of the differences between f and its approximation v xi n, where xi n is the largest number such that the rank of v xi n is less than or equal to n. This theorem has significant implications for the study of approximation properties in Sobolev spaces, particularly in the context of numerical analysis and computational mathematics. The subsequent sections introduce the linear operator S xi, which is defined as the tensor product of unidimensional operators. This operator is used to define a new polynomial subspace P1, xi, and to establish a connection between the approximation properties of S xi and the rank of S xi. Finally, Theorem 3.8 is presented, which is similar to Theorem 3.6 but applies to the linear operator S xi instead of V xi. This theorem provides further insights into the approximation properties of S xi and its implications for the study of Sobolev spaces. In summary, these sections delve into the approximation properties of linear operators V xi and S xi in Sobolev spaces, providing crucial insights for numerical analysis and computational mathematics. The theorems presented establish upper bounds for approximation numbers, shedding light on the behavior of functions in these spaces and the efficacy of approximation techniques. Here is a combined summary of pages 15 and 16. The authors investigate the right convergence rate of lambda n and dn, where lambda n and dn are the n-widths of the weighted Sobolev space WR2, W, ρ, embedded in L2, W, ρ. Specifically, they focus on the case where the generating weight W is given as an equation 1.1, with lambda equals 2, 4. The authors define the space our lambda W, ρ, as the set of functions f element of L2, W, ρ, represented by the series 3.1, with a finite norm. They construct a hyperbolic cross-polynomial approximation based on truncations of the orthonormal polynomial series 3.1. The truncation S** operator xi, f, is defined as the sum of f, k, pk over k element of g, xi, where g, xi, is the set of k element of nd0 such that Rl, r, k is less than or equal to xi. The authors apply the Tikhomirov lemma to establish an upper bound for lambda n and dn. They construct a sequence, xi n, infinity n equals 2 such that g, xi n, is less than or equal to n and sup f element of our lambda w, ρ, fs asterisk operator xi n, f, L2, w, ρ, much less than n minus r lambda, log n, r lambda, d1. This yields the upper bound lambda n, our lambda w, ρ, L2, w, ρ, dn, our lambda w, ρ, L2, w, ρ, n minus r lambda, log n, r lambda, d1. To prove the lower bound, the authors apply lemma 4.1 and construct a sequence, xi n, infinity n equals 2 such that g, xi n, is greater than or equal to n plus 1. They show that dn, our lambda w, ρ, L2, w, ρ, is greater than or equal to dn, c, xi n, minus r lambda u, xi n plus 1, L2, w, ρ, equals c, xi n, minus r lambda n minus r lambda, log n, r lambda, d1. Finally, the authors establish a norm equivalence between WR2, W, ρ, and our lambda W, ρ, for lambda equals 2, 4, which allows them to identify WR2, W, ρ, with our lambda W, ρ, in these cases. This leads to the main result, Theorem 4.4, which states that lambda n, WR2, W, ρ, L2, W, ρ, equals dn, WR2, W, ρ, L2, W, ρ, n minus r lambda, log n, r lambda, d1, for lambda equals 2, 4. The convergence rate of the right-hand side of equation 4.5 is conjectured to hold true for every even r. This assertion is supported by the work presented in this paper, which explores the numerical weighted integration of functions with mixed smoothness. The authors draw upon previous research in this area, including the work of Dinh on numerical weighted integration and weighted sampling recovery of functions with mixed smoothness. The paper cites various references that provide a foundation for the research, including the work of Dinh and V.K. Nguyen on optimal numerical integration and approximation of functions on R equipped with Gaussian measure. The authors also reference the work of S. Jha and D. Lubinsky on necessary and sufficient conditions for mean convergence of orthogonal expansions for Freud weights. The paper's discussion of hyperbolic cross-approximation is informed by the work of Dinh, V. N. Temlyakov, and T. Ulrich, while the section on weighted polynomial approximation in numerical methods for integral equations draws upon the research of P. Jungens, G. Mastroianni, and I. Notarangelo. The authors also reference the classic work of A. Kolmogorov on the best approximation of functions and the survey of weighted polynomial approximation with exponential weights by D. S. Lubinsky. The paper's use of mathematical concepts, such as the theory of weighted polynomial approximation and the theory of best approximations, is grounded in the work of H. N. Masker and V. N. Temlyakov. The authors also draw upon the research of E. Novak and H. Wozniakowski on the tractability of multivariate problems and the work of V. N. Temlyakov on the approximation of periodic functions. The paper's conclusion is supported by the references cited, which provide a comprehensive foundation for the research presented. The authors' conjecture regarding the convergence rate of the right-hand side of equation 4.5 is a significant contribution to the field of numerical weighted integration and approximation of functions with mixed smoothness.